Kusangpo and welcome to tutorial program or Loptenpa Lerim. Today I'm here to introduce an outstanding teacher of mathematics who has volunteered to showcase a few mathematics programs relevant to our students from class 7 to perhaps class 10. Hello, I'm Kazang Wangchuk, and sitting here with me in this beautiful setting of the Royal Botanic Garden in Serbithang is Melanie Bose-Lyon. Welcome to our program, and thank you for volunteering to produce some program.
Kazang, thank you very much for inviting me to take part in this series of programs. It is my intention to show you a series of programs that will focus on maths in the real world. We will look at a number of topics taken from grades 7 to 10, and we will have a look at where these topics are being used every day in Bhutan.
Tell us, how many programs do you intend to produce, and why exactly are we here in this wonderful garden?
We will start off our series with looking at a special program of interest. And this program will look at the relationship between how maths and nature are linked. The reason that we are starting in this beautiful garden today is because there are many examples of plants and flowers that we can use to start our investigation. Maths is often described as the search for and the study of patterns. It is hard to imagine that the seemingly random world of nature can be linked to mathematics. However, the links are everywhere if we look closely at nature's building blocks.
Okay, so what are we waiting for? Let's get started.
Let's warm our brains up with some well-known sequences. Firstly, take a look at this sequence. Yes, you guessed it. The rule or pattern is +2. Well done. Okay, let's have a look at this one. Let's try something harder. That's right. This pattern has a rule of ×2. Okay, more difficult again. Have a look at these two sequences. Well done if you spotted that the first pattern is square numbers and the second pattern is cube numbers. So finally, let's move on to the sequence or pattern that's most important for what we're going to be looking at today. Take a look and see if you can work out what is happening. Well done if you noticed that to get a term in this sequence, you have to add the previous two terms together. What you are actually doing here is looking at a very famous sequence. The sequence is called the Fibonacci sequence. This was discovered by a famous mathematician called Leonardo Fibonacci in around 1202. The sequence is very important in investigating how nature and mathematics are linked through nature's fundamental building blocks. So let's have a look at some examples of where nature is linked. So let's get started. Let's try and look for this Fibonacci sequence in firstly fruit and vegetables. To help us keep track, let's make sure that we've got the Fibonacci sequence in front of us. So let's start off by looking at the chili, a vegetable. If we look at the cross section of the chili by cutting it in half, we can see that the chili is made up of two sections, 2 being a number in the Fibonacci sequence. Some chilies are different. This one, the smaller chili, if we have a look at the cross section, we can see that that's made up of 3 sections, 3 being in the Fibonacci sequence. Okay, let's have a look at some fruit now, the apple. If we look at the cross section of the apple, we can see that there are 5 pips and 5 sections inside the apple. So also the apple is made up by building blocks from the Fibonacci sequence. Let's have a look at the tomato. The cross-section of the tomato we can see is made up of 3 sections from the Fibonacci sequence. And finally, the banana. The banana is also made up of 3 sections from the Fibonacci sequence. Still not convinced? Okay, let's look for more examples in plants and flowers. Let's start with this flower here. We're going to count the petals and see if the number of petals also is linked to the Fibonacci sequence. So this flower has 1, 2, 3, 4, 5 petals. 5 petals is a number in the Fibonacci sequence. Let's have a look at this flower. This flower has 1, 2, 3, 4, 5 petals again. You may think that it doesn't apply when we get up to larger numbers of petals. Well, let's have a look, shall we? This flower has 34 petals. Final investigation, we are going to have a look at the sunflower. Let's count the number of petals in the sunflower. 21. 21 also being a number in the Fibonacci sequence. We have done a lot of investigations this morning at the Royal Botanic Garden. Let's move on and develop the maths further and look for more examples in the human body. And for this, we are going to move to the hospital in Thimphu. To examine how this sequence applies in the human body, we need to take the maths of the Fibonacci sequence a little further. If you take any number in the sequence and you divide it by the previous number, you will find that you end up with a very special ratio. The ratio that you will find you end up with is a number that is somewhere around 1.618033. The higher up the sequence that you go, the more accurate the ratio that you will get. So, as well as the Fibonacci sequence being found all over the living world, we can also find the golden ratio all over the living world, specifically in the human body. Let's now continue our investigations and look for this ratio inside the human body. We are going to begin our investigation by looking at the hand. To find the golden ratio in the hand, we need to make a certain number of measurements. The first measurement that we are going to make is from the knuckle down to the end of the finger. This first measurement, you can see, is approximately 7.2 centimetres. The second measure that we are going to make is from the next knuckle up on the finger to the tip. And that is this measurement here, from that portion of the finger to the end. And we can see that that measurement is approximately 3.9 centimetres. So to find the golden ratio in the hand, we can now take the first number and divide it by the second number, and hopefully we will have somewhere in the region of the golden ratio, which is 1.61033. So let's do that. Looking at that ratio, we receive the number approximately 1.8. 1.8 is very close to 1.6, and we're going to talk about accuracies in a moment. Let's have a look for our second ratio in the hand. This time we are going to measure a relationship between the middle finger and the little finger. So first of all, let's measure the length on this skeleton of the middle finger. If I measure that, we can see that the length is approximately 7.8 centimetres. Next, I'm going to measure the little finger on this skeleton, and if I do that, we can see it's approximately 4.9 centimetres. So again, I take my large number, 7.8, and I'm going to divide by my smaller number, 4.9, and I end up this time with a ratio of 1.59, which is much closer to the golden ratio. There are many examples of the golden ratio in the hand, and you're looking for numbers very close to 1.6. Have a go yourself and see how many examples you can find in your own hand. We don't need to limit ourselves to just looking at the hand. There are many other ratios that we can find. First of all, let's look at the human arm. There are many ratios that we can measure in this arm. I'm going to show you one and then leave you to have the challenge of finding some more. The first ratio I'm going to show you is if you examine the distance between the wrist and the elbow, you can see that that dimension is approximately 24 centimetres. The next measurement we're going to take is from the tip of the finger to the wrist. And if I measure this, you can see that that distance is approximately 15 centimetres. So again, looking for our golden ratio, if you take the longer distance, which is 24 centimetres, and divide it by the smaller distance, which is 15 centimetres, we can find that we have a ratio of 1.51, which is very close to the golden ratio of 1.6. So let me show you another ratio that exists in the human body. We can measure the distance from somebody's waist to the floor and compare that as a ratio of their waist to the top of their head. So let's do that just now. So first of all, I'm going to measure from their waist to the floor. And if I do that, you can see that we end up with a measurement approximately at 93 centimetres. Next, I'm going to measure from the waist to the top of the head. This is quite difficult to do to get over the rib cage. But as I do that, you can see that we end up with a measurement approximately at 62 centimetres. So, if we then take a ratio of the larger length divided by the smaller length, so 93 centimetres divided by 62 centimetres, we get a ratio that is exactly 1.6, exactly on the golden ratio. So, as we've been looking at all these different ratios, not only in the hand, but also in the rest of the human body, we've noticed a few inaccuracies. We haven't always achieved 1.6, the number that is the golden ratio. And let me tell you why. As not everybody is made perfect, as we know. If you were to have a go at doing this investigation with your classmates, you would find that if you averaged all the results, you would have a ratio that was very, very close to the golden ratio of 1.6. We can even find the golden ratio in the human heartbeat. We can do this by dividing the time between main beats by the time between the main and echo beat. You can see this shown on the electrocardiograph reading. The resulting ratio will be very close to the golden ratio for any person with any heart rate. Moving back to plants again for a moment, we can find this golden ratio by examining the distances between nodes on a stem. The final part of our investigation leads us on to look at golden rectangles and how they link to golden spirals. A golden rectangle is thought to have a length that is 1.618 times its height. So if you take this dimension here and divide it by this dimension here, you should receive a number that is very close to our golden ratio. There are many rectangles that exist in nature, art and architecture that are built upon the golden rectangle principle. This is because it is thought that the proportions in a golden rectangle are aesthetically pleasing and balanced. Let's have a look, shall we, for a few examples of this golden rectangle. Now I'm going to show you how to make or construct mathematically the golden rectangle, and more importantly how from that we can construct the golden spiral, which has many important links back to nature. First of all, let's have a look at a deck of cards. If I select a card, any card, we're going to measure the dimensions of this card to see if it falls into a golden rectangle proportion. So the measurement across the top is approximately 5.2 centimetres. The measurement down the side is approximately 8.9 centimetres. So to find out if we are in the golden ratio here, we need to take the longer dimension and divide it by the smaller dimension and see what ratio we get. So 8.9 divided by 5.2, and the ratio that we get is 1.71, which is very close to the golden ratio number that we were looking at earlier. Let's take a look at another well-known rectangle that's used day to day. This time we are going to have a look at the bank card. Let's start again by measuring the dimensions of this bank card. And we can see that this dimension across the top is going to be approximately 8.6 centimetres. So let's measure down the side, and we can see that this dimension is approximately 5.4 centimetres. So to see if we are in the golden ratio, we take the longer dimension and divide it by the smaller dimension. And you can see that this time we have received a ratio that is 1.59, 2, and so it goes on. And this is again also very, very close to the golden ratio number that we were looking at earlier. There are many examples of this golden rectangle. I challenge you to go out and find some examples of your own. So now that we've found some examples of the golden rectangle, I'm going to show you how to firstly draw the golden rectangle, and then how to develop that rectangle into a golden spiral that has very many important links back to nature. So to start off with, we are going to construct a square. It doesn't matter what dimensions you make your square. I'm going to make mine 10 centimetres. So I'm starting with a line of 10 centimetres, and to make my square I'm using a set square, and I'm going to draw my second line at 10 centimetres. It's very important that you are accurate when you're making this construction. And then again for the top of my square, 10 centimetres. And then to finish it off. So there I have my square. So I now need to develop this into the golden rectangle. What I need for this is I need a set of compasses. And the first thing I need to do is I need to find the midpoint of this line. There are a number of ways that you can do this. You can find the perpendicular bisector of this line. Because I have a ruler, I'm going to measure the midpoint of this line, and I know that it's at 5 centimetres, and I know the midpoint of this line is also at 5 centimetres, and I'm going to draw that in very faintly so that it doesn't affect my construction later on. So at this point we're just going to label the square that we have made so far, and I'm going to label it LM O. The midpoint here is P, and then N. So now we have a square. We're going to develop that into our golden rectangle. So you need one of these to do so, a pair of compasses. I am going to set the arc of my compass at the dimension PM. And from there, I'm going to draw an arc. And I'm going to repeat this process from the other side of the midpoint line and draw another arc. Using a ruler, we are going to finish off our golden rectangle by extending this line through until it joins the arc. And we are going to repeat that process for the top line, extending it through until it joins the arc line. And then the final part of the process is that we can connect up those two ends together, and I'm going to complete labelling my golden rectangle by labelling that side Q and that side R. And what we have done here is we have completed a golden rectangle with golden proportions, rectangle LQOR. So, if you wish, you can measure this dimension and this dimension, divide one by the other, and you will find that you have the golden ratio. But what we are going to now do is learn how we can move this golden rectangle on to develop a golden spiral, which is very important, as I said earlier, in nature. So to do this, we need to subsequently divide our rectangle into smaller and smaller squares. So let me show you how this is done. We have already divided one large square off our rectangle. With what is left, which is this portion here, MQRN. So let's measure what dimension we have at the top here. So we have at the top 6.123. It's very important that you are as accurate as possible when you are making these squares. So 6.123 and draw a line. I'm going to do the same on this side and connect them up. And what I've done there is I've taken off another square and I'm left with a rectangle. So we are going to divide another square off what we've got left. So let's measure this dimension here, and that is 3.5678. So I'm going to measure along here 3.8, which is here, make a mark, and I'm going to do the same at the top, 3.8, and join it up to have divided off another square. Okay, so I've got one square, two squares, three squares, rectangle waste over. Yep, you've guessed it right, we're going to divide off another square from this rectangle we've got left over. So that dimension there is exactly 2.5. So I'm going to mark off another 2.5 here. Same on this side. And mark off a further square. And you continue this process taking off squares. So we'll just do this last one here. (1.2). And then we can do the same from what's left. So when you get to the stage where you can't really make any more squares because you've gone as small as you can go, then we can start to draw a special spiral. This is called a logarithmic spiral, and it is made by joining opposite vertices of each square. So let's start with the smallest square we've drawn, and we draw a spiral. And then we come and draw a curve, and continue to draw a curve, and another curve. And we keep drawing a curve between each opposite vertices of each square. And the aim is to try and make it as smooth as possible. And what you will find that you end up with is a spiral formation. This golden spiral is more common than you would think. In fact, it can be found all over the natural world. So today we have looked initially at an important sequence discovered by Fibonacci. We looked at the fact that that sequence forms the building blocks of nature, and we looked at examples in flowers, plants, fruit and vegetables. We've also learnt how to find the golden ratio by taking any number in Fibonacci's sequence and dividing it by the previous number in that sequence. We have investigated many examples of the golden ratio, including finding the ratio all over the human body by taking measurements and also looking at the human heartbeat. We have also examined the golden rectangle, and we have looked at examples and learnt how to construct it mathematically. Finally, today we've looked at the logarithmic spiral and how we make that from the golden rectangle. And the spiral can be seen all over nature. Until next time, I challenge you to have a look for more examples of what we have discussed today, and also to marvel over the fact that we have proved that nature is built on mathematical patterns and numbers.